Hi folks, and welcome back to Physics with Captain Rod here. I'm making this video here as a follow-up to vectors and vector addition. So hopefully you've seen my video on how to break vectors into components, but if not, I'll talk about it right here. So imagine we've got some sort of vector here that I've called vector A. This arrow symbol here means that this quantity is a vector quantity at an angle theta with the positive x-axis. So the idea of breaking a vector into components is to take this vector in the plane and break it down into its, I like to think of it as convenient directions. So this vector has an x component that points to the right. I'm going to go ahead and draw that in there. Whoops, I'm going to do that in a different color. And I'm going to go ahead and label that maybe AX for the x component of vector A. And it has a vertical component, or a component in the y direction, which I can draw like this. I'm going to go ahead and call that one AY. So the idea is that this vector, vector A at an angle theta, is equivalent to the sum of these two vectors, AX to the right and AY up. Now, I could have also drawn it AY up and then AX over. That doesn't really matter. I usually just draw whichever is kind of quickest and easiest. All right, so now as far as finding these here, and I see in picture number 2, I forgot the arrowhead here. So, all right, so here's my vector components again, AX, AY. And these can be found using basic right angle trig here. If we remember that the cosine function, the cosine of an angle theta, right, is defined as the side adjacent divided by the hypotenuse. So in this example, right here, here's theta. Adjacent to theta is the vector I've called AX. So if we write out what cosine theta is equal to, that's my shorthand for cosine theta, that would equal AX, that's adjacent to theta, divided by the hypotenuse. So the hypotenuse is the magnitude of A. I'm just going to write A here with the vector symbol left off to represent the magnitude of A. It's pretty easy math to solve this for AX, and we get the expression I've got right here. By moving the A over to the left, we get AX is equal to A cosine theta. Similarly, we can find AY from the sine function because the sine of the angle theta is defined as the side opposite divided by the hypotenuse. In this example, we would have sine of theta is equal to AY over A. And it's pretty easy to show by moving the A over to the left that AY is equal to A sine theta. All right, moving on. When we draw vectors for vector addition, so here's a pair of vectors, vector A and vector B. And in this example, vector A is, in the positive y direction. Vector B here has both x and y components to them. And the first thing we want to be able to do is draw the resultant for the vector addition A plus B. So I'm not used to working in Word here for this stuff. All right, so if I write this out, vector A plus vector B is equal to what I'm going to call the resultant vector. Graphically, this is what the picture looks like. Whenever you draw vectors graphically for a vector addition, they have to be tip to tail. Now notice in this picture, they're tail to tail. In this picture, the tip of vector A is touching the tail of vector B. And the way you get that is just by picking up vector B, plopping it down on the end of vector A. Then you can draw the resultant vector, which starts at your beginning point and ends at your end point. Now similarly, we could have also taken vector A, plopped it on the end of vector B. In this picture, we would have had like vector B and then vector A. We would have ended up right in the same spot. All right. This method is called the parallelogram method because when I take these two vectors here, like vector A and vector B, and I look at the vector addition, right? Again, these are tail to tail. To make them tip to tail, one way to do that is take vector A, which is this one, and then draw vector B right on the end. So in this picture, this one's vector A, this one's vector B. And you'll notice now they are tip to tail. I also can take vector B, which is this one, and put vector A on the end of it. Okay. In either case, I end up right here. And then you can draw your resultant in like I did in red, which starts at your beginning point, ends at your end point. Now when I do vector diagrams, I usually just draw half of it, like maybe the top half or the bottom half. But anyway, if you so desire, you can draw the full thing. This method is called the parallelogram method because when you do the picture correctly, you end up with this shape, which generically is called a parallelogram. Now, if vectors A and B were done to scale, you could actually measure the length of this, use your scale on it to determine what the magnitude of the resultant vector is. You also could measure this angle fairly easy with respect to the positive x-axis. All right, so examples. So here what we're going to do is we're going to add these two vectors. I've got this vector 10 kilometers long, 60 degrees with the positive x-axis. It's already drawn tip to tail with another vector, which is 8 kilometers long, minus 50 degrees with the positive x-axis. And what we're going to do here is we're going to start by taking these vectors and drawing in their components. I'm going to put their components in red. All right, so this animal right here, this 10 kilometers cosine of 60 degrees, I could draw its x component right, y component up. I could also go ahead and draw its y component up and then x component right. It doesn't matter. I'm going to go ahead and do this. All right, there's its y component. Let's see, let's call this vector A, and then we'll call this one AY. And then there's the x component for vector A. Now, it doesn't matter which angle we work with. You know, this is a 60-degree angle. That makes this one inside of here 30. This one also is 60, and it doesn't matter. Let's go ahead and just label this angle right here as 30 degrees. And that's coming because this sum is equal to 90. All right. We'll go ahead and come back to this in a minute. Let's come over here now and draw what I'm going to call vector B's components. Let's see, let's do this. There's the x component. And I probably got that a little long. Whoops. Oops. I forgot every time you change this, you have to go back and adjust your color. Thickness, I like 3/4. All right, so let's do this there. There's bx, by. And we'll go ahead and calculate those values in a moment. And I'm going to go ahead and draw the resultant vector. Oh, I did that in the picture below. There's what the resultant vector looks like. I'll leave it out of this picture then. Okay, so now it's a matter of finding AX, AY, BX, and BY. Go ahead and go back to my standard color for this. Now the idea here is you want to be able to do what I call tunnel vision here. You want to tunnel vision on these triangles independently. So for right now, you just have to focus on just this triangle. Put everything out of your mind except for this triangle. The side that I called AY is adjacent to this 30-degree angle, so we can use the cosine function to find it. So we can write out, okay, cosine of 30 degrees is equal to AY over its hypotenuse, which is 10 kilometers. Now we could have also used this angle. This angle right here would be 60 degrees, and AY is opposite the 60-degree angle. We could use the sine function to find it, but there's no need to. All right, it's pretty easy to calculate AY from this. AY is going to be 10 kilometers times the cosine of 30 degrees, which is 8.66 kilometers. This is a number we're going to need for later. All right, AX is opposite the 30-degree angle, so we can find that with the sine function. The sine of 30 degrees is going to equal AX over the hypotenuse here, which is 10 kilometers. So AX is going to equal 10 kilometers times the sine of 30 degrees, which is 5 kilometers. Now some things to notice here. We're dealing with vectors. We have to define directions. I'm going to go ahead and call like right positive and up positive for this problem. So AY is up. We'll consider that positive in this problem. AX is to the right. We'll consider that positive as well. All right, moving on. So now we need to focus on this triangle right here. And again, just ignore everything in the universe except for this triangle. The hypotenuse is the 8 kilometers. And I'm going to go ahead and just kind of skip to the important part here. So using the cosine function, because bx is adjacent to the 50 degrees, we're going to have that bx is going to equal 8 kilometers times the cosine of 30 degrees. Oh, I'm sorry, not 30, 50 degrees. All right, and I'm going to go ahead and get a numerical value here, if you'll just stand by for a moment. Okay, and I got 6.43 kilometers. I'll go ahead and carry 3 sig figs. All right. Similarly, we can find BY. Since it's opposite the 50 degrees, it's going to equal 8 kilometers times the sine of 50 degrees. Give me a moment here. I get 6.13 kilometers. Give me a moment. I'm going to go back and just double check this one. Yeah, okay. On second round here, I got 5.14 kilometers. I have suspected I did that wrong. All right, let's get rid of this. 5.14. I think I accidentally put 10 in here when I ran this, thinking about those. I'm just going to double check that one more time. 8 kilometers times the cosine of 50 degrees. Okay, 5.142 kilometers. All right, we're good. So the important numbers here are AX, which is here, AY, BX, BY. These are the numbers we need to find the resultant vector. In the picture below, I've drawn the resultant vector, which is here. Again, vector A and B are tip to tail. Now, the resultant itself can be broken into components. I'm going to draw those in red. I like my vector components in red for some reason. So here's the resultant vector. I could kind of draw it like this, like RY, RX, or maybe I think it'll be cleaner if I draw it this way. Here's RX and RY. Not the best triangle I've ever drawn, but good enough. And again, it's supposed to be a right triangle. There is some unknown angle, we'll call it theta here, that we'll find here in a minute. All right, the hypotenuse is the magnitude of the resultant. And we can find that by Pythagorean Theorem because, oops. The magnitude of the resultant squared is equal to Rx squared plus Ry squared. Now, the $1,000,000 question is, where do we get these things? And the answer is we get them by adding our previous work for these for vectors A and B. Rx we can get by adding the x component of vector A, which is this, to the x component of vector B. They're both to the right and they're both positive, so I'm going to go ahead and do this right here. So Rx is going to equal 5 kilometers plus Bx, which is 5.14 kilometers. We get 10.14 kilometers. Ry, right, the y component of the resultant we can get by adding the y component of this vector A. Let's see, which was 8.66 kilometers. To the y component of vector B, which is 6.13 kilometers, and notice it's down. So when you do vector addition, you have to take direction into account. Let's go ahead and put minus 6.13 kilometers. Now, getting back to this, whether we consider this positive or negative is not really important. What you have to realize is it has a direction. You can put that direction, take that direction into account by inserting a minus sign, or just doing something like this. The direction is down. This would have been a perfectly acceptable way to work this. All right. Oops. And next is to calculate a value here. Okay, I get 2.53 positive. Now we'll just make sure I added the right vectors. So AX is 5 to BX. Yep. AY to BY, and BY is down. Okay, we're looking good. So we got these vector components now. We know that Rx is 10.14 and Ry is 2.53. So let's go ahead and put these values in. So we're going to have R squared equals 10.14 kilometers squared plus Ry, which is 2.53 kilometers squared. And we'll go ahead and apply Pythagorean Theorem and see what we get out of this. Give me a moment here. I'm dealing with a phone calculator here. Okay, almost there. Okay, I got 10.45 out of this. Looks about right. All right, so what we have now is the magnitude of the resultant. That's this distance right here. We can find this angle using the tangent function. The tangent of the angle theta here is going to be the side opposite divided by the side adjacent. That's going to be 2.53 kilometers over 10.14 kilometers. And theta is going to be the inverse tangent of this ratio. So if you give me a moment here. Trying to find the second button on my calculator. It's a phone calculator here, so I'm not real familiar with it. Table redo. Oh, there it is. Okay. Oops. Okay, and I get about 14 degrees. Inverse tangent of 2.53 over 10.14. Yep, looks like about 14 degrees. And I just like to put DAS, which stands for direction as shown. That's 14 degrees counterclockwise from what I would call the positive x direction. You could also put a little picture if you wish, like here's the plus x direction, there's our vector r, there's the resultant, or there's the angle theta. All right, so this video is at 16 minutes here and going on 17. I think I'm going to stop that right there and start another one. I hope that this video has helped your understanding of vector addition. Have a great day.